Hi, my name is Levi. I'm the technical lead at our team CSH.
I'm Gloria and I'm a non-technical member.
My name is Andy. I'm alumni of CSH.
Nice to meet you all. I'm Patricia. I am an engineer. I work for Rolls-Royce, and I'm also from Romania, from Arad.
Okay, nice.
Hello, I'm Max. Also an engineer at Rolls-Royce as a graduate as well. It's nice to meet you all.
It's nice to meet you. Yeah. So since we heard you guys are both working at Rolls-Royce, yeah, that was like so cool. We couldn't wait to meet you guys, and we actually have a couple of questions for you. If you'll be okay with answering them.
Oh yes, of course.
Absolutely.
It sounds just amazing what you guys are doing. So, yeah.
So our first question would be, what inspired you to pursue a career in aerospace engineering?
We have pretty different answers for this. Would you like to start, Max?
So I've always been really quite fascinated and excited about like how cars and other sort of complex mechanical sort of systems worked. And I guess similar age to you, I took part in something called a Young Engineers Program. It was this international conference where we sort of like, you know, me along with like hundreds of other sort of like quite inspired students went along, and we learned all different disciplines of engineering. And the one that really stuck out to me became aerospace engineering. It seems like such a sort of like crazy and niche and difficult sort of industry to get into. But after that exposure in the conference, I found out that it's actually something that was very accessible to all, obviously with a bit of hard work. But it was something that became apparent to me that was really, yeah, I guess, I don't want to say, yeah, I guess accessible.
Everyone can do it.
Mm-hmm.
You don't have to be a genius to be an aerospace engineer.
Exactly.
You have to be hardworking.
Mm-hmm. You have to be a good team player.
Team player, yes, but
yeah,
yes, everyone can do it. For me, I'm very much different because I didn't necessarily wanted to do aerospace. I knew I wanted to do engineering because I was good at maths, I was good at physics. My parents, my grandparent everyone was an engineer in my family. So it seemed to me like, you know, my path was chosen for me, but I don't regret it. And I wasn't sure which type of engineer I wanted to be. So I just looked up what types of engineering there are in the world. And I was like, oh yeah, aerospace, that sounds cool. I'm going to do that. And it turned out I really enjoyed it. So it didn't come from a passion, it came from a curiosity for me.
Oh, nice. Yeah, that's really cool. But how do you guys came in contact with Rolls-Royce?
So we started while we were at university. So I went to University of Bristol, Max went to University of Nottingham. We both studied aerospace, and they were advertising roles for internships. And we both applied for a year-long internship, and we both got in, and that's how we met.
Mm-hmm.
Yeah, that's really cool. Also, what does a typical day look like for you guys?
So as part of the graduate scheme, Rolls-Royce really encourages to get a lot of exposure to different areas of the company. And the area that I'm sort of currently in is safety and reliability for in-service engines. So I deal a lot with problems that the customer comes to me, such as, I don't know, perhaps the engine is vibrating at a sort of like particular speed, and they are perhaps concerned about what sort of like how this impacts their sort of their product. So you become a little bit like a investigator, sort of doing a little research, and you come back to them with some quantifiable like risk which is associated with this. It's very fun, and it means you talk and you're dealing directly with customers themselves, but in an engineering context, which I find is the best of both worlds.
I am a performance engineer, which I know it doesn't mean anything to you guys, but basically what I do, I look at the engine as a whole and try to understand if our model of what we expect the engine to do is actually doing in the test. So my current role is to exactly look at that, look at the test data, look at our model of the engine, and see if they match. And if they don't, why don't they match? And I guess in my typical day, I go to work. We are encouraged and we like to go to work, although we can work from home. We like to go into work. We like to talk to people. We are usually there's quite a few meetings that we have to attend every day.
Yeah, well, that sounds pretty interesting. And you said you applied to work for Rolls-Royce. What surprised you most when you first entered the aerospace industry?
I think, despite how do I say? Sometimes it feels like what Rolls-Royce does is magic, in terms of how complex the product is, and it is scary when you just first join as a young intern. But the thing that surprised me the most was just how willing they were to sort of help you along with such challenges. So I think they know at the end of the day, the product itself has lots of criteria that it has to meet, and they really want to sort of help up the rest of the team and really push you towards completing your objectives, which was something that I never thought sort of would be like perhaps I guess they'd hold to such a high degree in that regard. So I think that's what surprised me the most, just how helpful and I guess welcoming they were.
Nice.
For me, it came as a surprise how slow the industry is. It might sound surprising, but if you think about the automotive industry, where they manufacture hundreds of parts in a day, we don't do that. It's a lot of because of there's so many safety regulations and it's such a complex industry. It takes a long time for a program to start from concept to all the way to.
Yeah, nice. But what actually makes aerospace different from the other engineering fields?
I think that regulation is a huge aspect. One bolt sold to a automotive industry might be, sort of a certain amount of, euros, pounds, but the same exact bolts with a certificate for aerospace industry is just, and the levels and scrutinize that they have to go through just certifying these individual sort of parts as small as a bolt can make the process really slow through regulation and really costly as well. And that's something you have to really factor in very early on into engine development.
Nice. I heard you said that one of the reasons you chose engineering was because you were good at maths and physics. But how important is physics in modern propulsion system design?
Well, I think everything is physics. If you think about how a jet engine works, there's like the core of it. I know there's plenty of parts, but the core of it, you have a compressor, an intake with a compressor that compresses the air and increases the pressure. Then it goes into combustion in the combustion chamber, which basically burns all that air with fuel. So the higher the pressure at the end of the compressor and beginning of combustion, the better, which then goes into the turbine, which the turbine drives the whole engine. So everything is physics, it's thermodynamics, really. Now, as an engineer, you might not be, really depends on what type of engineering you're doing, because you might be closer to all of these theory, or you might not. You might be dealing with requirements, or customers, or manufacturing, where thermodynamics and physics is not, you're not that involved with that, but ultimately that's everything.
But how much of your work is actually theoretical modeling, or is it more hands-on engineering?
Well, it depends what type of engineer you are. For me, it's all more theoretical modeling. I look at the test data. So they do a lot of testing of the engines, but I am not involved with that. And to be honest, most engineers are not involved with actual building of the engine. So we have manufacturing engineers, which you might think that's the people that build the engine. That is not correct. We have technicians that are actually doing the work. Manufacturing engineers are only basically telling them what the process is to building the engine or manufacturing, but we don't really touch the engines. We can go attend, see the test and engines on test, but we can't really go and screw a bolt in or do anything ourselves.
There's a really big push in Rolls-Royce in the last few decades to have everything more digital. And you've highlighted a great point, really. This theoretical to practical hands-on approach. It's very costly and expensive to, I have an idea, but how's it going to sort of work? To then just build it yourself and then test it at every single stage. So Rolls-Royce really sort of tries to take a step back and understand it through a digital, we call it a digital twin, because it's supposed to model the reality. And then when it comes to actually verifying that this product can do what it wants to do, then we usually build it and then test it in a very sort of in a scientific experimental environment, effectively.
I was very curious if your mindset has changed since becoming an engineering, and what do you think thinking like an engineer actually means?
I believe so. I believe I have my engineering brain on all the time. We literally fixed the couch earlier and we were discussing what the plan should be and how we should approach it. And I believe an engineer is a problem solver. That's essentially it. Regardless of the field, regardless of what you're doing, engineering means problem solving. And having an engineer's brain means always analyzing how can you improve and how can you tackle any challenges that you have, always making a plan in your head. How can I move forward? How can I do better?
Another aspect as well is you need to have a critical mind. If you receive data, you need to know, where did it come from? How old is this data? And why was it made in the first place? And with those questions, you could really sort of get more context, because some of the reasons why this sort of data, which becomes an assumption, why this data was given to you in the first place, because it could be based on old experimental sort of data or work that could have been vastly more updated solutions. So it's always good to be critical and scrutinize everything. I think that's something that I've used more.
That's something we were basically talking about it earlier. It's important to understand why, not just the what and the how, because we were talking earlier, we have a lot of specialists in the company that know everything about bearings or whatever, they know everything about it, and they have their own processes of dealing with things, and they would teach us their processes. But like these people have been doing the same thing for maybe, I don't know, 10, 20 years. And it's very important for someone like us, from like young early careers people that come in and ask, why did you do this? Why is the process the way it is? Is it because it worked 20 years ago? Maybe we have better tools now that we can adapt, you know? So it's always good to ask why, not just follow the orders.
And that's a very important, I guess, person you can kind of be within the team, something that's quite valuable, and something that as later you progress in your career, you're going to receive less of that. So it's actually quite valuable having sort of a young sort of engineers sort of like introducing to the team, just to keep that
freshness,
the lack of experience being an advantage in a way.
That even we encountered during our years in this competition is that while designing a mechanism or something, even if it doesn't work, we don't know if we should continue on prototyping or just leave it as it is. So how do you guys decide when a design is good enough and or is now no longer worth optimizing?
Should I say that?
Sure.
Well, that is a very good question. And often is like that question is asked at the workplace a lot of times. It's important to define requirements first. So once you have a requirement, you have to aim for that requirement. And as soon as you hit the requirement, you stop. Because it is important to understand that going beyond that requirement means investing more time or money or stuff like that, that yes, it can be better, but why would you make it better when that is all you need? Because let me give you an example. So in Rolls-Royce, we have what is called engineering drawings, which probably, like there's always, you design a part, a product, and then you send the drawing to the manufacturer to make it. And on these drawings, we must have tolerances. So I give you a length of 10 centimeters. I have to put there tolerance of 0.5 or, you know, and it's very important to really get those right, because it's easy to say, make a very tight tolerance. I want exactly 10 centimeters. But that means that every part that is 10.002 is scrapped. So that part is gone. That costs a lot of money and a lot of work and a lot of time. So it is important to get that exactly right. And if it's not that relevant, if it's slightly bigger or smaller, just leave it as it is, because it's very much a balance of how much time you put it versus how good it is.
We refer to the overall system that hits the benchmark's requirements as we call that the minimum viable product, basically. The absolute sort of like minimum that targets that you can hit, and then everything else could be a bonus if it's worth pursuing.
So yes, know exactly what you need and try to stick with that, because otherwise you just, you know, invest when it's not necessary.
Okay, that's interesting. Also, we heard from you that you have a lot of regulations. It's kind of normal to have all of those regulations in your field. We also have reliability issues with our robots, with our designs and all this stuff. And we would like to know, how do you test the system's reliability, and how do you, I don't know, approach these kind of problems that keep appearing in the design and the production phases of your product?
So I guess it ties in similar to what you were mentioning earlier with, like, for instance, an example being tolerances and how to sort of like acquire what sort of level of tolerance you can accept within your system. But what I do currently is quantifying how, if stuff does change from the overall design, how does that impact sort of like the system as a whole? Because obviously we can't have perfect parts and components coming through every day just to make up our engines. It's a difficult question to sort of properly answer, because every aspect of your job comes with reliability aspects of it, and each way that you interpret it, you can kind of work out a solution for all.
Mhm.
But yeah.
Sometimes there's like a solution for all is impossible.
Mm-hmm.
And I'm sorry, that's the truth. There's no one, there's no one thing that works for everything.
Yeah.
So I guess it's important to also be aware of which things don't have the same solution. So you invest time into dealing with them, basically.
Okay.
Yeah, so probably also during these tests of the system's reliability, what methods do you use actually to prevent component failure in extreme conditions?
So we have a lot of extreme conditions in the engine, as you can imagine. We have, so you have the combustion chamber, which basically burns at, I don't know, 1,500, 2,000 degrees Celsius. And then you have components there, metal components that have to withstand that high temperature. And normal metal would no type of metal would be able to support to sustain that without melting. So if you think of the turbine blade, I have a picture, a nice picture I can perhaps show. Sorry, I'm trying to figure this. Window, PowerPoint. There you go. So this is a turbine blade. If you look to the right, you can see there's incredibly hot gas coming in from the combustion chamber, and that hits the turbine directly. So what we do is we have these cooling holes inside each turbine blade, which is very crazy, interesting technology that has cold air coming into the turbine and then pushed through these tiny little holes. So then when the turbine is spinning, that air gets dragged on the turbine and creates kind of like a film all around the blade. And that's that's one of the things that is protecting the turbine from getting like melted, basically. We also have some coating on top, like ceramics or other materials that can withstand that temperature. But yes, it's very much a combination of things that work.
And to lead on from that as well, obviously being in such a hot and extreme environment, which is also spinning at several thousand revolutions per minute, that adds on extra considerations for how that overall system must perform. So an important aspect is if you have something so hot and spinning at such a high speed, as you can imagine, you have this growth. It starts to expand, not only from the temperatures, but also from the centripetal forces. And you can see on the right, a big problem we have is this tip clearance, because you must design a blade to fit inside this casing, and all the sort of like the tip clearance itself, you need to minimize as much as possible in order to get the most out of your engine, because you have performance losses if air starts to escape up and around over the blade, rather than in the direction where we want it to go. So that's a really big sort of consideration that you have to do in order to design all of these.
So we saw some kind of common points between our competition and what you're doing there. In FTC, we use belts, chains, and all this mechanical stuff. How do you approach power transmission inside an aircraft engine, and what lessons about mechanical efficiency could we apply in our field?
Would you take that?
Sure. So a very interesting project that Rolls-Royce has done is on
Ultrafan?
this ultrafan engine.
Yeah.
So this is effectively the largest engine that Rolls-Royce has or is going to be delivering. As you can see on the left-hand image, it's roughly about the same size as a sort of A320 fuselage itself. So it's enormous. And the reason why it can get so large is because of a key technology that we have with power transmissions. So if you look in the right-hand image, we have in highlighted, we have an planetary gearbox. And this is in order to have the overall fan size actually rotate slower based on the input from the turbines. So what we like is having turbines to run really quickly, but the fan, in order to get that, to optimize it and to have it sort of like spinning at a slower but bigger sort of radius, then we need to use a planetary gearbox. And I think that's where there's some key crossovers, because at the end of the day, this system is spinning extremely quickly, and it makes for quite a difficult engineering challenge solution. So yeah, this is what we're basically coming to face.
I can go on and explain exactly how it works, because I'm not sure how much knowledge you have in how the jet engine works. We basically, let me see if we put in a nice picture for it. This doesn't show much, so yeah, you have the suck, squeeze, bang, blow thing, but you also have to think about it as the turbine is driving the compressor. So they are both on a shaft. So the speed of the turbine determines the speed of the compressor. And then we have another turbine that drives the fan, the massive fan we have over here. And the turbines want to speed fast because that creates more energy, right? But then if we drive fast, then there's implication of how big the turbine blades can be, which you can see from that picture with me in front of it. It's quite massive. So we want a big fan, but the turbine that's driving really fast. The compromise, and they are on the same shaft, so they should be driving on the same, should be spinning at the same rate, which limits how big the fan should be. But if we put the gearbox in there, we can have the turbine spinning really fast, but slow down how much the fan is spinning. And that's why it's really important, because if you have the fan spinning slower, that means you can make it bigger.
Mm-hmm. Okay.
Yeah, I see. But how do you think engineering decisions today may impact aviation 20, 30 years from now?
Well, like I said, the industry is very slow. So we are probably making decisions now that will only happen in 20, 30 years from now. Investing a lot of money in technologies that are more sustainable. We are investing in technologies. Ultrafan, for example, is a very brilliant, efficient engines, like increasing efficiency by burning less fuel. That's one thing that we can do to make it more sustainable. We can also have technologies that we're exploring technologies that uses hydrogen instead of kerosene. We also have these SAF,
Sustainable aviation fuel,
which is basically made of
biofuel.
cooking oil or biofuels. So we are exploring a lot of that technologies, because it's important to be more sustainable, because these beasts are very, power hungry and very, very polluting. So one of the big pushes in 20, 30 years is to make them more sustainable.
I see. What was actually your biggest challenge since you guys came in this field?
Biggest challenge. There are a lot of challenges, like technical challenges at work that we have to overcome. We can't really think of. There's a lot of like the industry is so complex and there's so many things you have to wrap your head around it.
I think a big challenge as well. I'm going to give one technical and one non-technical. But when you are sort of new to this company and you are really trying to sort of drive your project forward, it's very difficult to know when to, I guess, sort of use the surrounding capability, such as like trying to ask for help, from advice from subject matter experts. So people who are very knowledgeable in many different areas of the industry, and just having the confidence to annoy them to the point where they help you out to sort of like complete a very specific task. And you realize that's just the way of life. You know, there can't always be helping sort of like all the time, but you've got to sort of make yourself, I guess, aware of sort of like, or make them aware of how much you sort of like require them.
Yes.
Okay. Thank you very much. I might have one more question left. This is also a curiosity. I don't know, from what I can see in automotive, you usually build an engine and then, I don't know, car manufacturers come and buy that engine from you and put it in their cars. Is it the same in your field? Like, do you build an engine and then Airbus comes to you, or do you build an engine specifically for an Airbus plane or Boeing or whatever?
So it's a bit of both, really. So
Okay.
we can have a partnership with Airbus. They want to build a new plane. We will provide the engine for them. But
Okay.
we most of the times we build the engines and they buy them from us.
Okay, I see.
So it is a bit of both, yeah.
Mhm.
And sometimes as well, if we have, so a lot of what makes Rolls-Royce quite, I guess, adaptable is we've changed as well. So say we've established a relationship with Airbus to make a certain engine to the customer. When we actually build it, we're actually building it at a financial loss as well.
Okay.
And it's the maintenance package that Rolls-Royce sort of has, which helps down the line make it into a profitable sort of business. So it's quite risky in a way. If there's problems which occur quite like, I don't know, medium or early on, then you can be at a real sort of financial loss. And that's if they, even if they buy the engines as well. Rolls-Royce in the 70s had a new engine design, and they were so confident it would be popular that they put a lot of money into it. And the problem was nobody bought it for a long time. And it was really difficult for Rolls-Royce to figure out what to do. We've got this really expensive product and nobody wants to buy it. So that put it in a very difficult position.
They almost got bankrupt.
Yeah, we were almost bankrupted
because of that project.
But then weirdly, interestingly, it then became the most profitable engine that they'd ever made until that point, like 5 years down the line, because of that forward thinking. But the problem is you are pushing yourself in such an extreme engineering and business, I guess, scenario that people might not see that vision early on. And you could be taking a huge risk. But yeah, a nice little story.
Well, thank you very much for being here with us. I think that was it from us. If you have, I don't know, any kind of questions for our team, we would be happy to answer.
What was the most difficult challenge for you guys?
I think Levi should answer this.
Yeah, so since each year we have a new game team that we have to accomplish. It's pretty hard because every year we have to come up with new ideas or with new things we have to build. And since there is this generational issue where there are new members coming and we have to teach them from zero, and then we have our mentors or alumni that stay alongside us and help us throughout the season. There is this hard part where there are times where we have to accomplish some tasks and we need like a little bit of guidance, and there are these hard mechanical issues or anything else that we encounter, and like because of the lack of knowledge because you're just high schoolers, yeah, there are pretty much a couple of times where we just look at a problem and don't know what to do. So yeah,
that happens all the time, not only in high school. It happens at workplace. You are faced with challenges you've never seen before. So this problem never goes away, unfortunately.
And a lot of the times you're faced with challenges your experts have never seen before. And they're like, well, then it's up to you then to try to work it out.
Yeah. And how did you overcome that?
Yeah, so with the help of our mentors right here, we can actually try and solve all of our problems because they are actually, most of our mentors are in this field of the mechanical field and engineering, and they usually know how to take the problem step by step and guide us through it. And even though they might know the answer and the solution to the problem, they are just giving us hints so that we can learn from them and try to solve them ourselves.
That's brilliant.
Nice.
That's brilliant. Yeah. And just maybe a curiosity, when you finish the project, do you write down your learnings so then the next year when other people come, they have your learnings and your advice in there?
Yeah, so each year, apart from the robot side, we actually have to make an engineering portfolio in where we write everything that we did on that robot, and not only. This engineering portfolio is judged by some judges at a competition. So it has to be divided in two sides. It's the technical side and the non-technical side. The non-technical side is more about events and community spreading and everything like that. And there's this technical side in which we have to explain each step that we made in creating the robot, in assembling it, in programming it. And we have to write everything that we do so that we actually show to these judges that we are making it and we know what we're doing.
Yeah, good. Because this is important, and not just for the portfolio, but for the handover part. When you step out and other people step in, they should have materials to read, and maybe even informal, just put your thoughts down on paper and share that with them. Because while it's fresh in your mind, in next year when they ask you a question, you probably won't remember. So that is something I would advise you do.
Something that gets told us all the time at Rolls-Royce is that the main value that engineers give to the company isn't just like actual products and stuff. It's the knowledge that you end up acquiring after doing all these processes. So it's all those reports and all those sort of documentation of your understanding and your outcomes, and importantly, how the next people can take over that task. That's where real value is added in a large engineering company.
Well, thanks again for being here with us.
Yeah, no, it's brilliant. We're happy to help. We are very excited for you, and yeah, all the best. And keep us updated with what happens, okay?
Yeah, we will, yes, of course.
Yeah, good luck. All the best.
Thank you very much.
Thank you very
Good
much.
luck to you all.
Thank you very much. Have a wonderful day.
You
Cheers.
too.
You too. Bye-bye.
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 Bye.